I'm Bradley Vargas. You can call me the Bradster. You've seen me in such fine quality, epic chemistry educational videos such as The Navy Uses Chemistry and Marines and Chemistry Don't Mix. Okay, we gotta finish up our gas stoichiometry problem, which is the whole reason why I'm doing this separate video for you guys. So we last left off in class. We took mercury 2 oxide and we were heating it up to get oxygen and mercury out of it. We don't care about the mercury, we're interested in the oxygen because we want to know how many liters of space it's going to take up. So they gave us 4.1 grams of the stuff. We know that HGO is 216.59 grams per mole. Pressure is at standard temperature pressure conditions, or stops traffic permanently. We find the moles of HGO, so there's 4.1 grams over 216.59. We walk away with 0.019 moles, which again, it doesn't sound like much, and really it isn't much, okay? We had to go and figure out moles of HGO to moles of O2, given it's a 2-to-1 ratio, so we did the proportion, you know, cross, multiply, divide, the Guerrero way. And you get 0.0095 moles of O2. So that's what we've got. Now we've got the moles, yay, but we have to figure out the volume. So this is where our PV equals nRT comes into play. So in other words, we need to solve for our volume. Okay? So for our volume, in this case, it's just going to be volume is equal to nRT divided by P. It's not that bad. It really isn't. We have the N, okay. We have the N from the previous problem. So let's go with it. So we had 0.0095 moles of our oxygen gas, right? And we are going to multiply that by our constant R, 0.0821, that's our constant. This is, remember, this is also why we have to make sure that our temperature is in Kelvin and that our pressure is in atmosphere. That's a very important thing, because if you work with torr and Celsius, your answer is going to be wrong. And that's not the Guerrero way, despite what Sean Guerrero is saying right now. Okay, with that, we also have our temperature, that would be 273. We're going to divide that over a big whopping 1 atmosphere. Okay, so our volume, ladies and gentlemen, at the end, when all the crying is done, 0.21 liters. And I know that Sally and Charlie would approve of this. So yeah, that's our answer for this particular problem, okay? So with that, let's go ahead and let's take a look at the second part. Let's take a look at the second part while I'm here cranking away on this video. Oh, and I bet you this is driving some people crazy, so I'm going to try to fill it. Okay, that might drive some people nuts. You'll have to live with it. Okay, so let's flip it up here on the back here. So our next question, they gave us another situation, okay, where it says at 400 Celsius and 740 torricelli. So the same amount of mercury 2 oxide, we're heating it up, but we're doing it under non-STP conditions, okay? So in this case, for us, for part 2, so we can go for number 2 here, our temperature is going to be 673 Kelvin. Our pressure, because remember, we're going to have to take that 740 divided by 760, and it gives us 0.974 atmosphere. Now, do we have to go calculate the number of moles? No, we don't, because we already figured out the number of moles, right? We already figured out the number of moles at STP, so the moles of gas isn't going to change. The only way that the moles of gas would change is if you opened up the flask and let some of the gas out, which they don't really do that in these problems. So we don't have to worry about that. That's the good news.
So it's the same N as
Part number 1. Because it's the Guerrero way.
Okay, so again, in this case here, we're going to take our PV equals nRT. This time, we're tracking for volume one more time, so it's going to be nRT divided by P will give us our second volume at non-standard temperature pressure conditions. Okay, but remember, now, this is still how an ideal gas behaves, so we can use the ideal gas law for this to work. What we needed was our number of moles of gas to do this. So with that, we're going to go ahead and let's plug it in. Okay, so we got 0.0095, okay, multiplied by 0.0821, multiplied by 673, because it's 400 plus 273, and the Bradster would approve. This is a 673, all over 0.974 atmosphere. Okay? So, multiplying this out, whoops. So we got this, okay? So we're just simply plugging in our values back into our equation here, and this is an 8. There we go. So we're just plugging in our values back in here, okay? And then we're just going to multiply it out, and we end up walking away with 0.5249 over 0.974. When we divide that out, our answer, ladies and gentlemen, is 0.539 liters. Now, how many significant digits are we looking at? Well, you could look at 2 significant digits on this one because they gave it to us originally, I believe, it was at 400 C. That's 1 significant digit. 740 torr, that's 2 significant digits. And the 673 K, 0.974, that's 3. So technically, we should be at 2 significant digits to apply the Odell effect. So this would be in 3 significant digits, but if we go with the Odell effect, we go with 0.54 liters. Now remember, when you apply the Odell effect, you do that at the very, very end of the problem, okay? I call it the Odell effect. It's named jokingly after a former student of mine in my AP Chem class. He is now off in, higher levels of education, but this is how it works, okay? Hey, I hope that this helps you guys out, and this is Bradley Vargas signing off. Highway to the danger zone.